Students, now let's try to understand the concept of rate law. Let's see what is rate law. For this, let's take an hypothetical equation. This equation will be helpful in understanding the concept. Consider a chemical reaction, hypothetical chemical reaction in which A moles of A is reacting with B moles of B to give two products, C moles of C and D moles of D. Now, this equation has hypothetical terms and we know these are number of moles. Now consider this to be a balanced chemical equation. That means it is stoichiometrical equation. Stoichiometry is maintained in this chemical equation. Now let's proceed and see what is rate law. Now according to rate law, it says the representation of rate of reaction in terms of concentration of reactants is known as rate law. This is rate law. It is also called as rate equation or rate expression. So this is useful in various other concepts. Now what? Rate constant. Let's see how this equation will be represented in that context. Now for this equation, the rate will be written as rate is proportional to the concentration of reactant 1A, and we have this place where we are putting X, and now let's take the concentration of reactant B. It has this power 1. Actually it should have been small a over here or small b over here, but it is not. This is according to the rate law. Actually these powers may be equal to the stoichiometrical values or may not be. It depends, actually it depends on the experimental data according to which the rate is determined. So this means that rate law has to be determined experimentally, not on the basis of stoichiometry of a chemical reaction. So again this will be written like this. Rate, now let's put constant K, rate constant, and again these concentration terms. This is for B, and we can also put it right like this, reactant upon T, K, so this is how it should be. Now looking at this equation, we can define rate law once again. Rate law is the expression in which reaction rate is given in terms of molar concentration of reactants, with each term raised to some power which may or may not be same. This is may not be same. It may be same, may not be same as the stoichiometric coefficient of the reacting species in a balanced chemical equation. Again, I am telling that this may not be equal because it depends upon the chemical data. First, this is to be experimentally determined, and then according to the data, it is decided whether this value will be equal to or not. These two values. It depends upon the practical availability of. So let's proceed with an example. Take a chemical equation in which NO reacting with O2 give we have this chemical reaction taking place in which, according to stoichiometry, 2 moles of NO reacting with 1 mole of O2 to give 2 moles of NO2. Now, we then collected data, we performed the chemical reaction, and then that formation of NO2, initial rate of formation of NO2 is put into this table. This table is also shown in textbook. Now, what information it is providing to us? Let's see. This is experiment number, and now this is initial NO2 concentration in mole per liter, and this column shows initial O2 concentration in mole per liter, and then the product NO2. It shows initial rate of formation of NO2 in mole per liter. So these are the experimental values. Now let's see. If we take a look at this value, now in this tab we are just increasing the concentration, initial concentration of NO2 to twice. We have turned it to double, though there is no change in the concentration of O2. So we are only changing the concentration of NO. So in that case, change in the initial rate of formation of NO2 is increased 0.384. Let's see how much 0.384 is. Mole per liter divided by 0.096. This value comes to be 4 times. Okay. Now let's see another example. Let's take data from first and third experiment. In these two experiments, the initial concentration and the final concentration of NO is same, 0.3, 0.3. But in case of O2, we have increased it twice. The concentration of O2 is twice. So let's see what happens to the initial rate of formation of NO2. In that case, it comes out to be 0.192 by 0.096 is twice. Now, we have in experiment 1 to 4. In the fourth experiment, we have increased the concentration of both the reactants NO and NO2 twice. So let's see what happens to the initial rate of formation of NO2. So it happens that 0.768 divided by how much? 0.096 comes out to 8 times. So this is when both the reactants concentration is doubled. Now if only the concentration of NO is doubled, we have 4 times increase. So this is going to influence the rate of reaction. So what we are doing? We can measure the rate of this reaction as a function of initial concentration, either by keeping the concentration of one of the reactants constant and changing the concentration of the other reactant, or by changing the concentration of both the reactants. So these results we got. Now it is obvious after looking at the results that when the concentration of NO is doubled and that of O2 is kept constant, then the initial rate increases by a factor of 4 times, from 0.096 to 0.384. So the rate equation for the reaction would be in that case sum other. Some other because it is depending upon the concentration of NO. So it could be written like this: rate is equal to, we have rate constant K, concentration of NO, and NO is twice the number of moles, and then concentration of O2. And now the differential form will be, for this reaction, D is equal to rate constant again now we observe that for this reaction, in the rate equation derived from the experimental data, the exponents of the concentration terms are the same as their stoichiometry. This is 2 and this is 1 for these two reactants. So this is how they are similar, but this is not the case for every reaction. It could be different because this is an experimental value which is obtained after performing a chemical reaction. So it may change.